We will start the program. I hope everybody has arrived. Do we have to wait for a few more friends of yours, or everybody is here? So I think we'll start the morning session. So today morning I'll be giving an introduction about the sample preparation and specimen preparation in particular for the EM, in particular in on single particle EM and cellular tomography at the end quickly. And then Steve would be taking over for the second lecture, and he'll be introducing some basics of TEM, and the seminar is all the lectures are live streamed online. So if you have any friends, you can message them to see if you want. All the lectures L1 to L23, and before I start the lecture, I just wanted to ask how many of you would be interested to go for an excursion on the Sunday 10th. If everybody is interested, just give your name to Abison. Abison will be there. You can give the name who is there at the back. You can give your name to him. So we will try to work out a budget for that based on how many people are there. Okay, and so I'll start the live session. So good. Today's lecture will be mainly dealing with specimen preparation for the EM. In particular, mainly we will be dealing with single particle EM, and at the end we will quickly go through cellular tomography. Cellular tomography, there is a dedicated section for cellular tomography on the 12th. Professor Baumeister, and before that there will be a lecture by Professor Lou Gan from NUS. So you will have more details on those sessions, but I will go through it quickly at the end. So cryo-electron microscopy is very analogous to crystallography. The steps in cryo-electron microscopy. Sample preparation is basically you purify the protein of your interest, and then basically you want to reconstitute in case of a multi-protein complex macromolecular assemblies. And specimen preparation is basically once you purify the protein multi-protein complex, you basically try to prepare it for the EM data collection. And today's talk, my talk, will mainly concentrate on specimen preparation. Data collection, so you can actually categorize in crystallography also into 4 steps, and I'm just putting an analogy to that. Data collection is in terms of crystallography, you do diffraction data collection, and you basically don't have the information of phase in that. But one of the advantage of cryo-EM image data collection in this is that you do have phases in the image that you already have collected. So the data has the phase information that is lost in the case of crystallography. So in that way, the phases are present and are derived from the native data itself in this case actually. Image processing and 3D reconstruction is analogous to data processing and structure determination phasing, okay, in crystallography. So this is briefly described in this article, which you will get in our data stick. Everybody will get a data stick. Yesterday it was a bit late, so everybody will get a data stick in which many articles have been downloaded. So in today's talk, I will be mainly concentrating on specimen preparation basically. So at the outset, I would like to thank Caroline for lending her slides to me. So most of the slides I will be using here as from her. So we will deal with basics of specimen preparation. There is a terminology which I always use as sample preparation for the first step, and the second step as specimen preparation. There is a purpose, because sample I treat it as purifying the protein and getting the complex. That I treat it as sample. And then once you have the sample, you prepare it for the data collection. That is specimen preparation. So I treat, there are some mixture of these terminologies with various scientists. So for me, reference is specimen preparation in this talk. Okay. So first we will deal with basics of EM grids and how we can treat them with various surfaces, how we can charge them based on the type of treatment that we have, and then we will go on to molecular EM. We will also briefly touch upon negative stain, which is one of the easiest method among the single particle cryo-EM. And then we will go on to cryo-electron microscopy, which is a bit more involved specimen preparation is. And then we will also look at how we can manipulate the sample in terms of treating the grid as well as in terms of manipulating the sample itself. And then we will briefly look at cellular EM. So to do EM, we have to prepare a sample which is visible, and we want to see something which is real, and that's the challenge. So when we want to see something real, if you want to see a protein complex in its solution, it's not possible directly in TEM without freezing the sample, because when you irradiate with the electrons, it's like bombing basically. So when you put electron on a specimen without treating it with cryo condition or negative staining, it's like basically bombing, and you destroy the sample. So we have to do that in a condition where it survives better. So one of the thing here, cryo-electron microscopy. In negative stain, you can leave with higher doses. So because your protein is actually lost, what you are seeing in a negative stain EM data collection is basically the scaffold of the protein. That is the mold basically, which we will talk in further detail in few minutes. So the specimen in the vitreous ice, so we will have to do in vacuum, because if we don't do in vacuum, it will contaminate the surface. Ice crystals will damage the crystal, as you will damage the specimen, as you will see in few minutes. We will go in more depth. So we have to minimize artifacts. So we have to compromise between preparing the specimen and seeing something real basically. So we have to minimize the artifacts. For example, negative stain gives lots of artifact by there will be a pressure on the molecule which will stretch the molecules in different directions based on the metal that we use basically. And then we want to see something real and want to actually see something basically. So we have to see, and if you want to actually see something, even if it is present, it has to be in certain way. For example, if the thickness of the ice is very high, you won't be able to see the particle actually. So the contrast is lost. And if the thickness is right, then you will be able to see the particle. In spite of this, you will be having a large amount of noise when you see the particle. So the signal to noise ratio in the raw data is quite high in EM images. So that's why we use what is known as class averaging to get several particles and put them together to enhance the signal to noise ratio. And another problem when you do imaging is that the particles move because of the local charges and the electrons that impart on the specimen. So because of that, there might be vibration in the substance on which the particles are set, or some local disturbances will cause the particle to move. So we have to minimize this movement as much as possible in order to get a high resolution data. So there are EM preparation methods. Topics considered are in 5 parts, so we will go through each one of them in subsequent few minutes. First one is the support that you use. Basically, this is the support on which the substance is laid basically. So for example, you have the substance or the specimen in a substrate. So substrate can be something which is usually hydrophilic, because if it is hydrophobic, your protein doesn't stick to it, and you will not see, it will go away to the other parts, so you won't be able to image it. So we need something many a times hydrophilic surface, so we treat them by some treatment the substrate is treated, and we will have to image the specimen. So this is I will call it as a specimen here. So we have to image the specimen which have particles in various orientation in the grid. So this distance will be around 3 millimeter actually, and you will see that there will be around 400 to 300 mesh of, usually it is copper grid, and on that support we have a substrate, usually it is a carbon film. There are variations to this carbon film. For example, you can use graphene single sheet, and there are other substrates for like gold, and gold also can be one of the substrate there. And we treat the carbon film, for example, by certain means which we will go in more depth, and then we have the sample over the treated substrate, and then we image the sample. Our main aim is to have the particles in as many different orientations as possible. There are problems certain times where you will have particles oriented in a particular biased manner, so which will create problem to do a 3D reconstruction, which we will come in a few minutes. How do we tackle those problems? The first is the support grid. Usually the support grid is made of copper, and this copper is basically mesh with 300 squares or 400 squares, or even less sometimes. Classically copper. There are possibilities of nickel, molybdenum, okay, and gold as well. Okay, so gold has certain advantages. Each substrate has some advantages. For example, copper is very important in conducting the heat, and they are non-ferromagnetic, so they are very inert to the electrons that passes through the specimen. Okay, and that's the reason most of the time we use copper here, and it also rapidly conducts heat. So the copper has a very good heat conductivity, so it rapidly conducts the heat away from the specimen. So the heat that is generated by the electrons is quickly absorbed by the copper, and the sample doesn't vibrate or go away from the position where it is. So the imaging is more accurate. And these grids have various shapes and sizes, and these are due to various requirements. For example, if you want to do a tomography, you need the spaces to be large because you are going to tilt, and large area is necessary. So the grid which you choose for tomography will be larger size. And for 2D crystallography, people sometimes prefer sparse hole, so the holes are separated very apart, and they take advantage of clean and ultra flat. Some of the grids which are very equidistant, like for example C-flat grids, they are used for such purpose. And based on the specimen and imaging protocols, grid metals other than copper are chosen. For example, if you want to do a cellular imaging, you may choose gold as a substrate because it's an inert element. So the substrate itself we will deal with now. So classically the substrate is made of carbon, which is basically a thin carbon layer of 7 micron, etc. It should not be too thick also, so it should be as much thin as possible, but yet it should not be so thin that it is vibrating when the electrons fall on it. So it has to be very steady, stable, and it has to be electron transparent, so it should not come in the way of particle as well. So it should be less disturbing for the particles, but at the same time it should be a supporting material for the particle. And it is carbon is very easy to prepare because you can use a sputter coater, and then you have gauges which to measure the thickness of the carbon that is coated. So you typically sputter it, and you basically lay it on the mica film, and then you float the mica film on the water, and then you take one of these 300 mesh copper grid and fish out the carbon basically layer that is laid on the water actually. So these are the ways in which you can lay the carbon on the grid, and then high purity of graphite gives better quality of the film. So you have to get best quality of the carbon source basically, which are basically sputtered. So basically the sample is laid on the substrate here, which is the carbon film, on the top of it actually. Continuous carbon film, thin or thick carbon film sometimes we use, and underlying plastic is usually retained, or sometimes it is removed. It's prepared without the plastic underlying film also sometimes. The carbon, what I was talking about, is a continuous carbon film, so it can be used both for negative stain as well as cryo-imaging as well. And in particular, people who do not want to have carbon in the background for cryo-imaging, they use what is known as Holy grids. So in this Holy grids, what is done is they punch holes at various intervals. It can be manually made in the lab as well. You will see the various ways of making Holy grids. And there are commercially available grids also, for example, C-flat grids, which have a very ordered position of a particular radius or diameter of the holes. So basically, you will have holes in the center. So you see that there is a copper grid, and on that you have a carbon film, and then in between the carbon film you will have holes here. So that is called as Holy grid, Holey. So this is an example of a Holy grid which is manually made in the lab. You can make it using a sonicator and firmware and other accessories basically. And the second one is the lacy grid. So this is also can be made in the lab easily, and these are also available commercially. And we can also make homemade regular 500 nanometer holes, which may be necessary for tomography. And C-flat and quantifiable grids are something which can be used for single particle imagings. So I regularly use C-flat grids for single particle imaging, where you know that the hole size is 2 micron and they are separated by 2 microns. So you can standardize the number of particles that can come inside the each hole basically. So basically there is a grid, there is a carbon layer with lots of holes on it, and inside this each hole you have the protein complex in the buffer of your interest, in the native buffer, and you basically freeze it in liquid ethane, as you will see in few minutes. So this is as far as carbon film. There are variations of carbon film. For example, sample where you want to control views for additional sample stability, a layer of very thin carbon over the Holy grid also can be laid. So instead of having continuous carbon grid and then having protein on it, you can have a Holy grid, and above that you can lay a thin layer of carbon, so that you have an advantage of reducing the number of proteins that can be used in a cryo condition. Okay. So if you want to use a particular protein complex in Holy grids directly, you may need probably 10 times more than the carbon laid C-flat Holy grids basically. So for example, if I use 0.1 microliter on a carbon coated C-flat grid, so 0.1 micromolar, then you may need around 1 to 1.5 micromolar with only Holy grids, without any carbon on the holes basically. So there are certain advantages. So variations of the carbon film can be used to tap these advantages basically. A thin layer of buffer plus sample between two carbon layers also are possible. So once you have this, I will call it a specimen. Once you have the specimen here, you can also lay another layer of carbon, so that it is sandwiched between the two carbon layers. Okay. So carbon flat or not, there are most of the purpose we need carbon film which are very flat, but there are cases in which you may need carbons which are not so flat basically, and we may need to deform the grid in such case. So we want to basically use a deformer, and then we press it on the grid, and then it is deformed. And the advantage of this deform is that with the preferred orientation may help to avoid high tilt angle. So if you have a tilt in the grid itself, you don't have to tilt the grid, so you don't need tomography tilt holder, or you don't have to tilt the fixed angle holder also. So you can keep it in the same position and then image, yet you get different orientation by basically punching a little bit of variation on the grid. So you basically deform the grid basically, and this helps in single particle where the particles go into a particular orientation. For example, many times when the grow is made a complex with the substrate molecule, they always go into the end views. Okay, so in such cases, this might be very helpful. So you can use it directly without using tomography as a single particle. You have a tilted view also as well. So the graphene is another carbon layer that can be used. It's a single layer, as you know about graphene. It's a single layer of carbon, atomically thin, but very strong. Conductivity, you can see this is a TEM image of graphene. You can see the atoms seen in the TEM actually. Conductivity at all temperatures, and they have low background compared to the conventional carbon grid actually. And each layer over standard Holy grid basically can be advantageous for having the sample on the grid firmly. So you can have a graphene layer on the grid, and then you can have the specimen and image it actually. So carbon film has certain disadvantages when it is frozen. For example, when you lay a carbon film on the grid, which is a bit farther away, then 200 mesh copper grid with a carbon which is sputter coated, basically amorphous carbon. So you see that there are what you call it as crinkling basically. So this crinkling of carbon can be seen. So reducing the size of the square or the holes can help in reducing this type of crinkling. Okay. Before freezing, this crinkling may not be there, so after freezing, this crinkling may appear sometimes. So differences in thermal expansion coefficient is the principle behind this crinkling. So if you have a linear expansion thermal coefficient for copper, the puckering can be explained by assuming that the coefficient of amorphous carbon is substantially less. So if you have the coefficient of amorphous material substantially less, then the puckering will be less. So this crinkling will be less actually. So the support and the substrate can be same sometimes. In this case, we can have made of similar material to improve low temperature stability and conductivity. So in this case, you can have both as gold actually, for example. So for example, cryo mesh has silicon carbide, and there can be gold grids as well, which has improved stability and better resolution of particles when we do a single particle cryo imaging and 3D reconstruction. So we have gone through each one of them: support, substrate, and substrate treatment. We will take over next. So substrate treatment, details of surface chemistry are poorly understood. So each specimen is very different. So for each specimen or the protein, we have to deal with differently on the substrate surface treatment basically. So for example, spreading, adsorption of orientation, all depends on the particle nature, the nature of the particle, and behavior of the grid on imaging is basically dependent on the substrate basically. And aging of carbon is sometimes thought of to be giving a better results than preparing a fresh carbon grid and imaging it in the next day. So there are different views by different people for this, but most of the time we prepare a grid and then use it after few days only. It's not immediately used actually. And when you want to use a grid, it can be cleaned by plasma. So plasma removes a top layer of the copper, the carbon layer that is laid, or you can also do a glow discharging unit. So by doing glow discharge, basically glow discharge is nothing but you have a specific atmosphere within the chamber, and you put the grids with the carbon surface on it, and then you basically apply a high voltage between the electrodes and the air inside gets ionized and they form a glow basically, and that basically ionizes the copper grid. So it is made, sorry, that basically ionizes the carbon basically on the surface of the copper grid, and this makes the carbon hydrophilic, and that renders it for the particle to bind to it in a specific manner when you put, so that it doesn't go away from the holes when we want to image it basically. So there are various ways in which you can charge this carbon surface. By air it is negatively charged, so we take advantage of sometimes if the protein is his tagged, we basically glow discharge and then the his tag binds to the surface and the protein is localized there wherever it is binding. For methanol also, if you keep methanol in the chamber when you do glow discharge, you can charge it negatively. Methylamine can be used to charge the grid positively. Okay. Treatment of UV, treatment with electrons, for example, are the other ways to basically prepare the substrate. Okay. Another way to prepare the substrate is that once you have a prepared carbon surface, you can also use additives like polylysine, which gives positive charge on the surface, and detergents also can be used for membrane proteins in particular if you want to use, or nickel NTA lipids can be used. So EM preparation methods, the sample which is prepared are laid over the grid so that you get the specimen ready for data collection. Okay. So now we will see the negative stain, how it is done, what are the advantages of negative stain, pros and cons. The sample is surrounded by heavy metal solution and forms a die cast actually around the protein. So when you actually image the negative stain, the die cast is what you are going to see, and the region where you are going to see as a less contrast is basically the protein region, which doesn't have protein anymore actually, in fact. Okay. So it is basically you are making a die cast. For you might have seen people in pottery, they make die cast and then they break the die cast to get the cast, isn't it? In this case, we make the die cast and the cast inside is lost because you dry the cast. When you dry it, the protein inside loses its shape and it's lost, and you won't be able to see. Okay. What you are going to see is the scaffold or the metal cast that you are going to see. So that is a negative stain, and that's the reason why it's called negative stain, because the stain sits where protein is not there basically. Okay. And ideal property, one of the biggest advantage of negative stain is very high contrast compared to cryo imaging, high density, and because of this only it is high contrast. Stability, you have a higher stability, so you don't really use low dose for this. Many times you just go and do the data collection without low dose. But most of the time, since cryo people are used for low dose, we usually collect negative stain in low dose mode actually. So solubility and ability to fix the sample. Okay, these are all the ideal properties for the stain basically. So you should have good solubility for the metal. Okay, uniform spreading on the support film, and structureless when dry. So the structure of the dye should not affect the proteins per se. Okay, and chemically it should be inert, so it should not interact with the protein of our interest basically. So basic protocol, what you do basically is absorb the sample, okay, on the carbon grid, carbon film, and then you basically blot the solution and the protein is there. Before the protein dries off, you should immediately add a cast of heavy metal and apply the cast of heavy metal in solution such that it is there before the protein loses its shape or solubility basically. Okay, so you have to quickly blot it and immediately put the negative stain on the sample. So typical concentration for a negative stain is you usually have a carbon grid and you have a 0.1 micromolar of this protein complex. This is the protomer density. So you should basically have around 0.1 to 0.2. Based on the trial and error, you can actually adjust the concentration of the macromolecular assembly on the negative stain grid. Okay, and then apply the heavy atom stain, typically 3.5 microliter to 4 microliter on the blotted sample. Okay, as soon as you blot the sample, immediately you apply 3.5 to 4 microliter of protein dye, negative stain, and then blot and leave it for drying. So when I say blot, it's nothing but basically you apply the sample and then blot with a filter paper. There are various pore sizes of filter papers. You can choose between them for the various negative stain. You can use different pores. So we apply this sample on the grid and then we blot with a filter paper. Various pore size are for the filter paper are available, which can be used to control the way in which the blotting is done. Okay, there are various ways in which you can blot. You can lay the forceps on the floor and then you blot it with the filter paper with your hand, or you can lay the film on the floor and then you take the forceps with the grid here and then touch the filter paper. Okay, various people prefer very different ways. I do this way. There are other ways of preparing the grid as well. So you can have the sample here as a true droplet. So you basically smear on this and then you smear on the negative stain as well. Okay. So pros and cons of the negative stain specimen preparation is you basically prepare the specimen within 5 minutes. It's very easy as compared to cryo. So no specialized equipment is necessary, as you will see in few seconds. There are specialized instruments, but it's not necessary. And need only a small amount of sample, good contrast, that is the biggest advantage. Sample protection or fixation, time resolved, we can adjust according to our need, but whether it is only after the 3D reconstruction, whether it's visible or not, we will know. Time resolved, if it is domain swapping or something, we can be able to see, but if it is helix movement or something, we won't be able to see because the resolution of negative stain is limited by the cast, which is around 15 to 20 angstrom at the best. So can give quite detailed information, including from the raw images. So you can look at the raw images and then actually see and say what is the oligomeric state of the protein. Easier to see very small molecules. There is a bigger advantage of this, and that's why sometimes if people who want to do cryo, they combine the cryo with the negative stain. So cryo negative stain is used to see smaller particles, and reconstruction is possible in this. So most of the new beginners start off with negative stain, do a 3D reconstruction, and do everything from beginning data collection to the 3D reconstruction, and then go on to the cryo. Cons: view a cast of sample, not sample itself, and dehydrates and flattens the and distorts. So this is what I was talking about earlier. So it has a disadvantage because it can since it dehydrates, it can flatten the protein sample, and sometimes it can positive stain as well. Okay, so we have to be aware of that, and also it can partially stain, so you may not be able to see other domains. And several commonly used stains have extreme pHs, so it may be not suitable for proteins sometimes. And in the best case scenario, resolution still is limited by the negative stain grain size basically. So strongly recommended for a new sample. So the negative stain is, whenever you do, as I said, first step is to do a negative stain and check. So there are various negative stains. One of the most famous negative stain is uranyl acetate. There are ammonium molybdate, phosphomolybdate, and tungstate, and there are various other substrates, and there are pH ranges at which they can be used. Okay. One of the most important thing when you do a negative stain is that you have to filter the sample. Filter the negative stain solution after you make the negative stain stock basically. So filter it, and then you can use it for a longer time. 22 micron filter is used to filter the negative stain. So getting the most out of the negative stain, so this is an example of negative stain. So you see a kinesin and microtubule. So you can see kinesin on the microtubules here, and this is a microtubule alone without the kinesin motor. This is another example from this paper. Benefits for large dynamic multi-protein component. Basically, you can see multi-protein component here, dynactin and dynein and the microtubule. Okay. So let's go on to from negative stain to cryo-EM. Cryo-EM is a process in which you freeze the specimen sample. You freeze the sample in a solution which is in its native condition, and then the buffer around it is made vitrified basically. So it should not form ice crystal. That's the main aim of the cryofreezing. It should not form ice crystal, rather it should form a vitreous ice. Like in crystallography, you use cryoprotectants. You can use cryoprotectants if you get ice crystal. So ice crystal destroys the protein, and you won't be able to image as well. You will see a dark background there. So what is vitreous ice? Basically, the solution that is used is amorphous. So it should not diffract, it should not become ice crystal, whether it's cubic or hexagonal lattice. It should be a amorphous solution when it is frozen, basically. Ice crystals destroy samples, and means it can be placed in vacuum of EM column. So it has to be placed, as I said when I was talking in the first few slides. The low temperature cryo-EM is taken in the vacuum, and some cryoprotection from the radiation damage. So this ice also protects the specimen from the radiation damage. How is vitreous ice formed? So this was developed by Jacques Dubuchot in which year? 19? Yeah, I have the reference paper in the list of references. You can go through it. So this process has to be done very quickly, and it has to be done within fractions of seconds, so 1 millisecond, and that means that you have to have a cooling rate of 100,000 degree per second. It can be Kelvin or centigrade. So at atmospheric pressure forms below minus 160 degrees. So it has to go from room temperature to minus 160 within fraction of seconds. Okay, and requires a rapid freezing rate and avoid other phase transitions. So it should not go into crystalline form. So it has to go to amorphous form directly. And rapid freezing, a thin layer of sample is also essential. So when we freeze, it has to be thin. So the blotting has to be accurate when you freeze the sample. So you basically, a grid is placed on a cryoplunger at the tip of the forceps, and then you basically blot either manually, or pneumatic devices are there to control, or electronic devices are there to control, and you blot it, and then and have a typical thickness which is less than 2000 or 3000 angstrom, and that is to be frozen as a amorphous. So this is a basic equipment. As I said, we don't need a expensive setup here. So this is a setup which is which is exactly the same as the setup that is there in Birkbeck, which I used earlier. So this was made here manually. I took some parts from Birkbeck, but this was made here, and in India this can be made at a cost of around 40,000 rupees, less than that. It can be homemade actually. If anybody wants the size of and the dimension, I can give you. But as I said, this can be easily made. There are very expensive options as well. You will see in the next slides. So this is basically, you apply the sample here, and then you basically blot it, and then you plunge it. So you can have a leg control. You can easily get a gadget of where you can press a button on the leg, and then it basically plunges into liquid ethane here. Okay. So cryo-EM grid basically is, you have the grid, and then you apply the sample, and then you blot it, and then you have a certain thickness of sample, and then You plunge freeze it immediately in the liquid ethane. Why liquid ethane? Because it is very quick in conductivity basically. So very thin sample layer means rapid water evaporation. So it has to be quickly plunged into the liquid ethane. And performing freezing in humid atmosphere helps many a times. So you can have a chamber surrounded with humidity. And so this is an example of how the humidity affects the size of the layer. So for example, at 4 degrees, it is 5.2 angstrom per second. That is the rate of evaporation. And at 25 degrees room temperature, it is 4 times that actually. And at 60 degrees of humidity, which is a typical case for any lab, example in Trivandrum, it is around 60, 64 degrees humidity, high humidity. That's an advantage for freezing cryo, but it's not a good for freezing protein crystals basically. So if you want to freeze, the rate of evaporation is basically 207 angstrom at 4 degrees at this humidity, and 807 angstrom per second at room temperature. So this is from communication by Caroline with Ken. These informations are personal communication. So the cryogen liquid with melting point should be minus 160 degrees or better, and liquid nitrogen boiling point is minus 196 degrees, and melting point is minus 120 degrees. Okay, so boils in thin layer around sample and insulates it. Okay, this is called as Leiden force effect. Okay, for example, propane melting point is minus 189 degrees, and certain other solution like ethane melting point is minus 180 degrees. Ethane and propane are flammable, so we usually use liquid ethane for freezing. So you basically put a liquid ethane and surrounded by a liquid nitrogen solution there. Okay, you have a small heat coil. We can put the heat coil inside and then keep the liquid ethane as liquefied, because if you leave it for a longer time, it solidifies as ice basically. So these are the expensive option, but there are definite advantages of these because it is controlled, and you have more repetitiveness is more assured in this. So if you prepare a grid, 3 grids in 4 grids may be better for cryo-EM than when you manually do. It may be 1 or 2 grids among 4 when you do manually. So the repetitiveness and reliability is more. You can control the humidity within the chamber, and that's a big advantage as well. Helps new users also, so it can be easily done, and improves reproducibility at least on same machine basically. So while cryofreezing, the main aim is to form vitreous section basically, vitreous solution. Basically solution has to be vitrified. It should not form hexagonal ice basically, or cubic ice. So here you can see this is a part of hexagonal diffraction pattern. So you can actually remove the objective lens and see the diffraction. If you see this diffraction, you know that it's a lot of ice there. And if you see a diffraction pattern like this, then it's a hexagonal ice formed there. Okay. And both crystalline forms of ice are less dense than liquid water. Their expansion can damage biological samples as they form basically. Okay, yeah, it's 1988. I was searching for this year. So once the specimen is ready, the grid is ready, cryo-EM grid is ready, it is mounted on a cryo holder. Okay. So this cryo holder, there is CT3500 from Getan or 626. These are the type of cryo holders where you have a small lever, and it is temperature controlled through a metal rod which goes to the tip of the grid, basically tip of the rod where the grid is mounted here. So you basically insert this cryo holder into a cryo station, and then you basically have liquid nitrogen covered everywhere, and you have the small grid holder. Basically the grids are kept here, and they are basically moved into this region, and then you transfer the grid into the holder, and then you lock the holder. There are various means of locking the holder. You can screw it, or you can pin it up directly, push it up with a pin. And then the lid is closed. Basically, you have to close the shutter. Basically, there is a small shutter which is closed so that you keep the liquid nitrogen temperature when you take it out in order to insert the holder into the TEM. So that is a very crucial stage. Basically, when you are taking out, it has to go into the microscope rapidly, as quickly as possible, without damaging the holder. So, and if you damage the holder, it's very expensive holder, so something like 30 lakhs. The holder itself is in Indian rupees. So cryo-EM grid cartridge loading system. So there is a definite advantage of this cartridge loading system, because you can load multiple samples at the same time, and there is a better stability as well. As this is FEI Polara, the machine that is there in IICT Calcutta right now. The only machine, Polara machine in India for biological TEM actually. And a typical 200 kV machine also, which is there in IIT Delhi right now, can be used for this purpose. And the setup is you insert a height cryo holder like this into the TM for imaging basically. So there are other, so now as of now FEI Polara is not available, so the newer models have come, so this is this model is not available basically, but it's an advanced version of this. So advantage here is that you can have the sample autoloader, and also you will have the DVAR filled automatically, so the refilling is automatic. You don't have to refill the DVAR every 1 or 2 hours. So here you have to refill the DVAR with liquid nitrogen. So every 1 or 2 hours, if you refill, you have to wait for 5-10 minutes in order for the grid to settle down in order to image again. It can be sometimes half an hour, 1 hour as well, sometimes. So this is an example of a cryo image from kinesin motor on a microtubule. You can see a microtubule and the kinesin motor on that from Carolyn's lab. And this is an image of cryo-EM GrowEL in complex with Rubisco, non-native protein, which I did. And this is a negative stain of the same, which is a mutant version, which was used as a mutant version to enhance the side views basically. So we had a problem with the substrate bound GrowEL, which went into end views. So we used a mutant D473C mutant version in order to induce the side views. So maybe I will be talking about this in a little bit more depth in heterogeneity. And this is the cryo-EM image of the complex, the same complex. So you see that there is a big difference between the contrast. Here the contrast is white, and here the contrast is black here. The particle is white here because you are seeing something which is a vacant region. Okay, so the rest is the metal cast. Okay, and so usually this is the convention for image processing. You flip the cryo image to opposite contrast basically. So the protein will usually is kept as white region. So the cryo images are flipped, and then the image processing continues as usual, like negative stain. So this is an example of the 3D reconstruction that we made. So this is APO without the substrate, and you can see a substrate very clearly bound here, which I will talk about a little bit more in the later seminars. So you get a 3D reconstruction, pretty decent 3D reconstruction with the negative stain as well as the cryo image basically. In this case, we were not able to get any good negative stain imaging because for some reason stain was affecting the substrate, I think. So we were not able to get in negative stain. So we had to do only cryo, and in the cryo only we were able to see the substrates basically. So pros and cons of cryo-EM. Physiological condition is the biggest advantage of cryo-EM. You have high resolution information from the imaging if you have a considerable good sample, and then information about the sample itself, about the internal details, all are available from the cryo-EM, and the phases are available, which is the biggest advantage. 3D atomic resolution reconstruction are not theoretically, practically possible nowadays. So atomic, I will call it as better than 3 angstrom. In this case for cryo-EM. So 2.2 angstrom is the latest structure by Venki Ramakrishnan, and Better than that? Sriram, sorry, Sriram Subramaniam, and yeah, that is the structure of beta galacticides, yes. And sample protection is the best in the cryo method because it is the native condition. So there are advantages of cryo over crystallography that people talk of sometimes in papers, that you have the structure in solution state basically in cryo, because it is frozen at a very rapid time scale, in millisecond scale. It is in native condition basically. Capturing of transient intermediate is also possible, so you can time the freezing point and then you can capture at various stages of the reaction basically. The negative downside, it is slower because it is painful to make a grid and then insert a grid into the holder and then holder inserted into the microscope. It takes some dedicated time compared to negative stain, at least an hour basically. And in terms of, in the case of negative stain, it just takes 5 minutes to make a grid and then load it, another 2 minutes, that's it. So need more sample than for negative stain. So if I use 0.1 micromolar for negative stain, you may need 10 times more sample for a cryo imaging, because you basically look at the holes and the protein has to be inside the holes. Poor contrast is the biggest problem. The problem is partly overcome by class averaging basically, by improving the signal to noise ratio by putting look-alike particles into classes, basically 10 particles together, and then you improve the signal basically. Requires more specialized equipment, as you saw, and sample is very electron sensitive, low dose imaging essential. So we need to always image it in low dose condition where the dose is less than 15 to 10 angstrom per, less than 10 to 15 electrons per angstrom square per second. And low temperature is protective as well for the sample which we have in the frozen state. So the specimen is ready, and we have in cryo condition made the specimen, and then it's ready for data collection. So the rest of the things will follow in the subsequent lectures. We will go on to a combination of cryo and negative staining. So to improve the contrast while retaining sample hydration, people use a mixture of cryo and negative staining. Sample less beam sensitive can increase dose and therefore further improve contrast. And from grain size, stain penetration. So that is one of the limitations of the negative stain when you use along with the cryo. So basically you prepare the protein and then apply the sample onto the Holy grid, sit the grid on the drop of stain, and then you blot it and plunge freeze it. So this is an example of ammonium borybdate which is shown in this paper. So sample perturbation and creates disturbance in the imaging. So there are many various reasons. It may be induced because of the beam, which is electron beam that falls. So for example, you can see that there is a movement in this, okay, and this movement correction can be made afterwards. So vitreous ice is an insulator and leads to charge accumulation. So because of this charge accumulation, when the electron forms, it gets disturbed actually, and because of this disturbance, it basically causes a drift in the image, and then the image that is formed has to be corrected for that movement basically. Changes in carbon film and electrostatic effect on beam. All these are basically problems in doing cryo-EM data collections. Now solutions is that use correct detectors. So there are direct detectors nowadays in order to do the image movement corrections basically. And imaging protocol, for example, sometimes you may use pre-exposure for 0.1 seconds or milliseconds. So pre-exposure can be used. Just cast an electron beam for a fraction of seconds, and then you collect the normal data. So that stabilizes the grid for some time. Treatment of carbon or thick carbon, increasing the thickness of carbon may be a solution for this. Or reducing, as I said earlier, you can reduce the hole size to increase the stability. or other materials as well, example graphene. So this is a example of from Luri's lab where they have shown that gold grids are substantially advantageous than the conventional amorphous grid or carbon grids. So you see that the resolution of this is increasing better in the gold actually. So number of displacement is very less in the case of gold grid, and you also see that the RMS deviation is very less compared to other methods, amorphous carbon and the graphene example. So it is better than graphene as well, gold grids. Of course, it should be expensive since it's gold. So summary is that the gold grid nearly eliminates beam-induced movement, inert, non-toxic, highly conducive, uniform electrical conductivity, and thermal contraction. And there are certain consideration: optimum thickness, thicker layers make no difference basically, and surface treatment or blotting the same, measuring defocus, no thorn rings, so considered alternatives. Okay, no motion correction needed, and cost basically. So as I said, these are the concerns basically. Thorn rings may not be visible because you don't have carbon grains, so that is a disadvantage basically. You cannot estimate before data correction. These are the disadvantages basically. So I think I should stop here because the time is overlapping. I'll quickly finish off in 5 minutes. So these are the steps which we have gone through one by one. Okay. Some of the other factors when you prepare the specimen is or the cryoprotectants, buffer in which detergents, salt, cofactors. Because of this and the stains that you use sometimes may dislodge the oligomeric states. So these are the constants that you should be aware of when you are preparing the specimen. I'll skip this, but this will be there in the slides which will be given to you. You can talk. Okay. More complex samples, large dynamic multi-protein complexes, large organelles, cells, and all these biological entities are large and structurally unique. So they are structurally unique, so it cannot be sampled. So it has to be one instant. So it has to be frozen and imagined in the various orientations so that you get the 3D reconstruction at the same instant. So you use electron tomography, and Professor Baumeister and Lugan will give more extensive deliberations on these topics later. So this is basically a tomography method for cellular tomography method. This is the in vitro tomography of human epithelial axonems by Lin et al. In 2014. This is structure obtained by them. Some of the consideration is that whether you need metal fiducials so that you can use those as marker for obtaining the tilt angles, and benefits of gold grids demonstrated by these people. So for tomography, gold grids are advantageous. All these things will be dealt by Leica Ian. There's a scientist from Leica who is going to talk about these things, chemical fixation and other fixation methods. So I will not go into the depths so that I can quickly wrap up. So basically the goal is to modify the cells to allow section and observation. So you cannot image sections which are more than 5000 angstrom. So you will not be able to get a contrast. So you basically use sections and you images and get the various section images of the specimen basically. So without using fixation, there are other ways of freezing the sample and then directly sectioning. So these are the most wanted method. People are trying to solve protein structures within the cell using these methods in the native form. So it doesn't require resin embedding or anything. So this is a case where free substitution is done. But the next case where
hello sir, my question is that regarding that deformation of your grid actually, if we deform the grid actually, will there be any problem in about the eccentric height when we are focusing the beam actually? will there be problem in setting up the eccentric height?
It depends. If your grid is not on the same level, then there will be a problem in eccentric height.
So as we are
If your deformation is basically changing the height of the grid also, then there will be this problem will be there.
okay.
Yeah. So that is inevitable. If you are doing a grid deformation, there will be some change in the eccentric height which has to be taken care as and when you go to that region.
So is the cryo crinkling the same as grid deformation? Can you use it analogously?
Cryo?
Crinkling that you mentioned.
Yes. Crinkling is there in the case of when you have a carbon film. So if you don't have a carbon film in the holy grid, then that crinkling will not be there. So in that case, you will have to go sort out.
Is it similar to deformation?
Yeah, it's very similar to that. You can.
So, the second question is in negative staining. You said small molecules can also be looked. What do you suggest?
Yeah, it will increase the contrast of the small molecule.
How small? I mean,
you can go better than 180 kilodaltons, smaller.
Okay.
So usually the limit of cryo is 180 kilodaltons. That's what is known right as of now. But there are certain special cases also available, like 67 kilodaltons that we heard about yesterday. Elena was mentioning.
Hey Naresh, thanks a lot for this nice overview of specimen preparation. I have just a question, and please correct me if I'm wrong. You mentioned that you do your negative stain thing using low dose. Yeah,
many a times we are used for cryo-EM data collection.
Not just for cryo, for negative stain. I mean, you mentioned.
Many people who are used for cryo-EM data collection, they use negative stain itself to do data collection in the low dose itself to do data collection in negative stain, basically.
I'm just curious, have you ever looked and compared the images, how they look like? Because low dose, can you get that better contrast?
Yes, it should be possible. Yes. Okay. All the data collection that I specifically do is in low dose, basically.
Mm-hmm. And you also showed your cryo-EM structure, and you mentioned that you couldn't look these particles in the negative stain. Can you briefly comment on it?
Can you come again?
You also showed your cryo-EM structures, and you mentioned that you can't look them in negative stain properly.
Stain, yes.
Can you briefly comment on it?
Yes.
Why you can't see them in negative stain?
There are reasons for that. We don't know the reason, but what we speculate might be that whatever we picked the particles, the side views in the negative stain were not having substrate. That might be one of the reasons, because the stain dislodges the substrate from the GROW-EL. Well, that's one possibility. Another possibility is that the particles that we picked itself may not be having, but some other particles. For example, we always pick the side views, and the side views may not be having the substrate in the orientation in which it was visible for 3D reconstruction, basically. So the end views might be having the substrate, and it was indeed the case. Actually, we were able to prove that the end views have the substrate in that case, actually. So that's the reason.
Okay, thanks a lot.
Close. In addition, higher salt concentration will affect the staining.
Higher concentration is?
Higher salt concentration will affect the staining?
Yes. Salt concentration has to be as minimal as possible. It will affect various metals, basically. Yeah,
so
definitely.
Is there any special buffer system required for staining?
Different stains have different requirement. So lesser the salt is a general procedure for negative stain. For anything, for example,
so
even for protein crystallization, the minimal salt, the better it is. But it is inevitable if you want to keep the protein in solution sometimes to have higher salt concentration. So in those cases, we have to use them. So you choose a different negative stain metal compared to what is not compatible for that.
Thank you.
So what is the alternative of thorn ring, and how robust is that for gold grids?
I don't know the answer for that. Maybe Elena may be able to tell. Alternative for thorn ring for gold rings. So
for gold grids, what is the alternative of Thorn rings and how robust is that?
First of all, with gold grids, you can observe the tone rings as well. It's not the problem to see tone rings. The question is how well the sample will stick to the gold grid. This is a challenge. But in any case, Chris Rose, who is working with Laurie Passimore, he did quite a lot extensive research of that, and he made quite interesting approaches. The problem with gold grids, they're not sticky. Sample doesn't like to stick to the grids. It's not the question of tone rings. You can observe them. And he has suggested some technique how to use it, and in this year in method of the enzymology will come a new, it's right now in press, it should be out quite soon, a new review on how to make the gold grids and other approaches make sticky.
Thank you.
Sorry, I thank you for the nice talk. I just have a few questions. And the first one will be like, since recently, and we have one new holder like liquid cell. And I don't know, I'm new in the field. Have any, it's, since you have mentioned this, I don't know if it's useful for the cryo studies without freezing, like using liquid cell directly.
Mm-hmm.
Do you think
I'm
it's
not
possible?
aware of it. You're saying that there is a new cryostat that is developed for...
No, I mean liquid cell means you have liquid directly to get liquid.
Oh. Okay. Okay.
Do you think it's possible to use this one instead of freezing and have? I don't know.
I personally, because the electrons, as I said, it's very invasive. If it is in liquids, it will evaporate the sample actually. Membrane. Okay. It prevents from evaporation.
In general, when the guy from Leica will be here, it's really would be useful to discuss this issue with this guy. In general, what people are using, it's high pressure freezing.
High pressure freezing.
High pressure freezing, what they're using for their large cells, etc. And then actually after that, when it was high pressure freezing, possibly it would be make sense to do something like FIB, focus ion beam milling of the sample, and to look at that in scanning microscope. But it's difficult how to say. I'm not a specialist exactly in this area, but when the guy from Leica will be here, it would be the best way to.
Yeah, I'm concerned
okay, it
about
doesn't.
That's
exactly. You have to freeze if you want to do electron microscopy. The sample.
You don't have. That's what he said. There are guys working on a liquid stage, which you can actually image a liquid in the beam.
By definition, what we have in electron microscope is vacuum. In vacuum, the sample has to be fixed. Yeah. Yes, I don't understand what you are saying, but that's it's some kind of controversy between. You want to look something which is alive in liquid, but nonetheless the conditions of electron microscope, it requires everything to be in vacuum. How you give the sample in vacuum?
It's a new holder that now in material science, people studying
You mean that it has a specific chamber?
Yeah, they have a thin silicon wafer, that's a super thin, that can allow electron come in and go outside, or even come into the top and exist from the bottom. And for sure, you get a reduce of resolution. But think for our project, for the cryo samples, even we have a rough model in a live, it's amazing, right? Even liquid, it's a new observation. Even it's in micro, I would say a nanometer scale. It's resolution is perfect already. So I was thinking, have two questions about this. Have anybody tried, or it's possible? And for sure, it's going to be more damage in liquid, and it's more movement in the liquid sample. But
it's much more dynamic.
Yeah, but anyway, we're fighting for the limitations of the electron beams, right? Trying to use as low dose as possible all the time. So we already.
But nonetheless, it depends how thick your sample in general. How the
they have a thickness judgment. Our holder like from 100 nanometer to 5 micrometer.
It's
the judgment depends on the.
I don't know how well it's transparent.
But it's
5 micron. It's quite a lot.
That's interesting. No, I mean
probably
it's still in the development stage. That's why it's not known.
So it's my
Look, everything in development. Looking forward to your good results.
Okay, thanks for that. Second question is very basic actually. For the FIB sample, you said we can further modify or cut the sample after freezing. Yes. So that should be FIB focused IMB operation should be done in cryo ICM, right?
Yes.
Cryo state.
Yes.
So
it is done in cryo condition. Yes.
Okay. Okay, that's it. And I have 2 comments actually, if I have time.
Yes,
one comment about eccentric height. But I think for the banding grid, if the eccentric definition of eccentric height at the beginning, I think from material science part is about when you kill the sample, the sample doesn't move. So like a geometrical center of the goniometer called computer state. So actually when we change the sample holder, change the grid, from different manufacturing, the thickness of the copper will be slightly different also. So you always need to judge the right focus a little bit, right? So it doesn't matter if you bend the grid a little bit or not. It still needs to judge the focus of your image. And the second comment will be of their comments about the copper and the gold film. The first ring comes from tone ring from gold is 2.2 angstrom. So for our resolution image, we are fighting for tone ring is like when you have high resolution image, you do Fourier transformation from the contrast transfer function, you get, or not, from the latticing, you get the reflection rings.
So when you basically do imaging, you have a objective lens. People will talk about Thorn rings in the later classes. I think Steve will talk, I think. So in that, if you remove the objective lens, you will see the diffraction basically.
Yeah.
Okay. And that diffraction rings basically is Thorn rings basically. And that can be generated if you have an image generated theoretically as well. So for this resolution, what is the ring? And then we can compare the image with that, and then we can see how much resolution in the image, actual image, do you have actually. Good.
Yes, but the largest spacing, from
carbon. Specimen also itself.
You mean from?
Yes.
But from this copper, it's a gold film or the crystalline, right? It's crystalline gold. Okay.
If you are slightly mixing up 2 different issues.
Okay.
So one issue of the diffraction pattern of the supporting film. Supporting film, if you think that the gold is crystallized, then it's a diffraction pattern like in X-ray crystallography, and it corresponds to the spacing in the lattice and the gold. And if you told right now that the distance is about 1.2 angstrom,
2.2 angstrom,
then exactly where the reflection goes. But the tone rings which you are discussing typically, it's a diffraction pattern of the point spread function of the image. Point spread function, point spread function of the microscope, it's a so-called the mean, how every single small dot in the microscope is distorted by the imaging formation system in the electron microscope.
Oh, okay.
It's not even the object. It's how the perfect dot of the sample image has been distorted by the image formation system in the microscope. It has been modified. And what we are looking like a tone ring, it's a representation of the Fourier transform of the point spread function of the microscope. You are changing the focus, the point spread function has been changed. And the tone rings reflects and related how, for example, defocus, astigmatism, whatever. It's 2 different issues. And very often with our point spread function, right now with the modern, with modern detectors, with modern coherent beam in the microscope, we are so happy when the tone ring goes to the 2.2 angstrom. Look, and where's your gold rings? We are talking of different things and very, very eager to see tone rings up to 2 angstrom.
Okay, I see the point. I understood now. I'm sorry for the misunderstanding. Maybe it's about the material science part comments. Okay. It's a different side.
No problem. It's just good. So the last question, Benelli.
Freezing?
Yes. So
repeat the question.
So do you have any trick on the grid to align the polymer, for example, microtubule on the grid? So basically, you basically have the protomer, then you apply on the grid. It will be in various directions, isn't it? So you just imagine. Do you need it to align, because it's done by image processing. You can have it in any orientation. Yes. 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 So that is done through reducing the concentration, so they don't overlap actually. If they are overlapping a lot, then the concentration of the polymer is, the protomer is reduced. Then you get separated. And that imaging you can actually, in whatever orientation it is, you can do a imaging alignment. So you can bring it to the vertical position or whatever the horizontal position you want to do the 3D reconstruction. This can be aligned. Good. Thanks. If there are no more questions, I would like to thank myself. Thank you.
If there are any questions, you can discuss with the speaker later. I request Professor Orlova to present this memento to Dr. Natesh.
Your talk is later. Thank you.
Organizer of this wonderful school and workshop, and I wish you good success in the future.
It is an honor for us you to come here. Thanks a lot, indeed. Thanks.
So,
And before you go for tea, please give your names for the Sunday excursion, whoever wants to come. And the plan is basically to go in the morning to a poor island and go on a boat in the backwaters, and then have a lunch there in one of the restaurants. It may be floating restaurants, not sure yet, depending on availability, and then come back here. And you are free in the afternoon to go around in Kovalam. You can go to Kovalam beach. You are free by yourself to explore Kovalam a little bit on that day. Okay, that's the plan. So whoever wants to come for Puvar backwaters can give their names to Avison, who is there on the left hand side of me, on the right hand side of you. And tea is served outside, and please be back in another 15 minutes. We are running late actually. See you then.